are exactly the same. Well, the identity function is a perfect example of that because it maps 0 to 0, 1 to 1, etc. And so its domain and range are the same. And then what's something whose domain and range are not the same? Both of those. Because the range of the 0 function is only the value 0. The range of the successive function is the positive natural numbers. So it's not the same as its domain because it converges on all natural numbers, but its range is at just the positive ones. So that's some examples of things that you might have that might be useful in showing a function is non-trivial. Once you show it's non-trivial, then you actually look at it, at least I would do this, and I'd say, can I use one of the simplified versions of Rice, one of the weaker forms, like domain or range associated with it? Well, what could you use in this particular one that might be useful? Could you use either of those? I used purely their I/O behaviors are exactly the same, but could I have simplified this one? Could I have simplified? If two functions have the same range and one is a constant, what can you tell me about the other one? It will be a constant, right? Okay. And if two functions, so it turns out I could have used the slightly simpler version on this one. Let me go through what I actually used. Yes, sir.
But what if, like, they diverge at some places, but they both have the same range, but maybe one of them diverges?
Yeah, that's just saying that all I'm saying when I do that is if two happen to have the same range, will they both belong to this? And this one just says, it doesn't say they converge. Oh, it does say it converges everywhere. Okay, if I'd chosen one where I said if it converges, it's the constant. You're right. So that's why I had to use this one, because I left out, I was thinking I allowed it to not converge, but if it converged, it was the constant. Okay, so I can't use that one. So I have to use the stronger version in this case. So what I do is I just say let f and g be two arbitrary functions with the same I/O behavior, and that just means for all x they give you exactly the same value where they converge and they diverge at exactly the same places. And so now what you have is if f belongs to constants, then that means that there exists a k such that for all x, f of x is equal to k. But what that says is if you set this particular value of k to be c, there's got to be some value associated with it, then what do you know about this function? If this one gives you some fixed value of c for every input to it, then this one will give you the exact same one because it converges and gives the same result. But that means if I can write down a constant there, then there exists some constant such that for all x, g of x equal to k. But that's exactly the definition of g belonging to constant. So in this particular one, I can do an if and only if proof. But in this one stage, what I have to say is there has to be an instance of that constant. And I just pick that and say, I don't know what it is, but there's got to be some instance of it. And so I say, well, since this has exactly the same input-output behavior for all x, it'll give me exactly that value. And then I can pull that out and say, oh, that means there exists some k such that for all x, g of x is equal to k. In which case I actually have the definition of constant. Yes, sir?
Do you need the g of x equals c step? Do you need this step?
Do I need that one? I won't get fussy with you. A sort of formal proof would say you should do that. You should say there's some instance of k, and we'll just call it c. But will I be that fussy in grading it? No, to be honest. So, but this is a more precise proof than just jumping to there from that one. Because you have to say, why does there exist a K? Well, because there was some instance of this, such that f of x gave you that value, and so g of x gives you that value. But
can you use K immediately?
I mean,
Can you use K immediately?
I wouldn't use K because it's an instance. There exists K.
Right.
I don't know what K is, so I picked some value and called it C.
You know it's equal to the 1 for f of x though.
I mean,
because of the way you define g of x, you know it's equal to the 1 for f of x. So
yeah, I agree with you. Skipping that step is, I'm not going to be that fuzzy. But in formal proofs, this is a correct step. Helps for me to have better balance, doesn't it? But there's not enough room for me to fall down. I once was giving a talk at Carnegie Mellon, and they were taping it, and I walked right off I walked across a wire, a cable, and I got to watch myself fall because there was a video recording going on in the back, and so I think it's the only time I've watched myself, although I've envisioned it many times. Okay?
the question
So,
was, did you laugh?
Pardon me?
Did you laugh?
Did I laugh?
Did
Yes,
you laugh when
of
you saw
course I
yourself
did.
fall?
I thought it was funny.
Then there you go. That's
Yeah. My clumsiness is something that's been with me. I can remember back to 4 years old. So I'd say it's been with me for a while. Almost 70 years, that's long enough, right? You gotta learn to live with things. Okay, the other thing I would do with a problem like that is typically, and I may not go both directions, but for the sample I went both directions. What I might do is just ask you to show that constant is no harder than total, or I might ask you to show that total is no harder than constant. But for the particular thing here, I went in both directions on it. So to go from the case where I say I want to show that constant is no harder than total, and that turns out to be a little bit harder. Because what could I do for the other direction that's so trivial? I won't even put up the overhead. Let's say I asked you to show total is reducible to constant. I don't want to put it up because I want you to tell me how to do it. Yes, sir. Your pen was up.
You could define GF to equal f of x minus f of x.
Right. And zero's a nice constant, isn't it? It's a great constant. And if it diverges anywhere, then it's not a constant because we chose this thing to be such that if it diverges, it won't fall into our category. So that's perfect. So one direction is absolutely trivial. What does it show you if total is reducible to constant? How complex is constant? Not RE and it's not co-RE, because total is one of those things that requires to quantify it. For all there exists. But showing that total reduces to this doesn't show it's as equivalently hard to total. You have to go the other direction, and that's what this does. This shows that constant is no harder than total. Okay. And to do that one, there's a whole variety of ones to do it. The way I set it up is I said, well, I need to pick, I don't know what the constant is, but I know if it's a constant, it will produce that value at given f, the input 0. You know, so all I do is to say, let's define this thing, g of f of 0 as f of 0. Well, if it diverges there, it wasn't a constant, life is good, I've taken care of it. But just because I have that, I haven't proven it's a constant. So what I do is at each stage up the line, what I try to do is I check it and say, hey, were you the same? Is f of y plus 1 the same as f of y? Now what the least y z does, since z is not in there, that will do an unbounded search if that turns out to be false. So it will diverge if that's false. Otherwise what will happen is it will converge and it'll just produce the answer fy plus 1. But I didn't have to do that. What did I have to do? Just make sure the bloody thing converges. That's all I ever had to do with regard to this. So that's just sort of being playful when I decided to do that. The least z would be fine. What value would it end up giving you? Yeah. If it's a constant? 0. Because the least z would be 0. You feed it 0 and it would come back as, okay, I found true, so it must be at 0. So I didn't really need to do that, but in any case, what happens in this is if f of y converges and its value is the same as if f of y plus 1 is the same as that, then I'm going to end up converge. I'll get back 0 from this thing. And in my particular case, what I'll end up doing is producing another constant function. Just for fun, I did that. So my function will be a constant if the other one was being constant. Otherwise, what's going to happen to it? It's going to diverge at some place, and once it diverges, it's going to diverge forever beyond that particular point. Because it's always going to fail. Well, not entirely true. How would I make it always fail? Let's say I wanted it to fail every point afterwards. How could I do that? What if I change that from f of y to g of f of y? So it looks at the previous value of g of f. What is the previous value of g of f? Well, it's whatever f was at that point in time. Unless f didn't meet my rule of being f of y plus 1 being the same as f of y. Then what will it be? It will be divergent. So if I made this just minor change to this, and I come in here and change that to g of f, I'm just showing you for all sorts of, I want to do one construction and show it. So if I change that, it will still have the property that I was looking for. It will converge everywhere if and only if f belonged to constant. But now what will it do? Once it diverges, it'll diverge everywhere past that point. Why might that be useful? What would be the property? What if I asked you to reduce constant to infinite domain? What will be the domain of this if the other function wasn't constant? It'll be finite. Yeah, well, all finite are enumerable. That's absolutely true. Yeah. But the idea is finite versus infinite. And so the only way it can be infinite is if it's got to have converged the previous step and said, I like you, and it's got to do that all the way down. Whereas if I compare f of y to f of y plus 1, it might miss at one step. But then at the next step, 2 steps later, it says, hey, everything's cool now. I'm back on, and it would converge. So if I had a problem that had to do with finite versus infinite domain, this construction could be useful. Just trying to give you a bunch of different examples with it. Okay, back up. This one. Okay, this is the trivial one. We already did that. If what you're trying to do is reduce total to constant, my favorite constant is 0. And if I was trying to reduce total to monotonically increasing, what would I do that I'd change in this? Let's say I had this property called monotonically increasing, and I wanted to show that it's at least as hard as total.
Add y.
You're absolutely correct. Perfect solution to it. That is monotonically increasing. As a matter of fact, it would end up being the identity function, which is a great monotonically increasing function. And if I asked you a question to say, prove that monotonically increasing is undecidable using Rice's theorem, what's the first step you do? Prove it's non-trivial. So what's monotonically increasing? Identity function, successive function. What's not monotonically increasing? Constant zero, you know. That's why I'm saying they just pop up all the time. And then what I could do, what's the next stage of it? Well, if I have two programs that have the same input-output behavior, don't try to use domain, don't try to do range, because it really does matter how it does its mapping. It's got to be growing all the time relative to its whatever input you give it. It has to have a larger value than if you gave it a smaller input. So that is an input-output property. And if you have two functions and one's monotonically increasing, then what do? Is you say, well, if it belongs to that, if f belongs to it, then that means for all x, f of x plus 1 is greater than f of x, right? But if g has the exact same mapping behavior, then for all x, g of x is greater than, g of x plus 1 is greater than g of x. But what does that tell you about g? It belongs to monotonically increasing. So I could take this proof here and I could do just slightly simple modifications to it, and that's another problem that I can show is undecidable. Pick one for me related to this. What's a function that's non-decreasing? What does that mean? It means for all x, f of x plus 1 is greater than or equal to f of x. Could you do that? It turns out that it's okay to map it on something that's monotonically increasing, because that will fall into the category. So I'm just showing you can take a proof like this, make a minor modification, and then use it in a ton of other places. Okay. So these are just some examples.